And so now we come to the final section on distributions and weak solutions. Okay. Distributions and the ideas in the that we defined for distributions underlie a lot of the working. So we already saw how the convolution with the fundamental solution considered as a distribution explains very quickly why the convolution with the inhomogeneous term gives a solution to the inhomogeneous equation. And so that is just one example of the ideas of distribution underlying the course. But as I said in that previous section, you can also just, once you have the idea of what the solution should be, just go ahead and directly prove that it is a solution without bringing in a lot of the distribution theory. And that's the course that's what we do in this course to avoid too much work with distributions, which can be a bit tricky. So it's important, therefore, to understand the idea of distributions without necessarily having to do so much of the proof of distributions. So let's go through their definitions firstly, and then we'll see how they're used, because we also have this notion of weak solution that comes up a few times in this course. So the definition is all in section 2.4. For a function, we have what's called its support. So you take all the places, all the points that this function is 0, and you take the closure of those points. Actually, that is the reverse of the definition. Good work for spotting that. You take all the points where the function is not 0, and then you take the closure of that set. So, for example, if you have, this is the most typical example, you have a function of that looks like this, a bump function. And so between here and here, it's not 0, and then outside, its support is this closed set here, right? Including the boundary, even though f is equal to 0 on the boundary, it's in the closure of the points where it's non-zero. Okay. And we speak often of functions of compact support because the support of a function is by definition a closed set. It's the closure of something. When we say a function had compact support, is what we're really saying is that the support of a function is bounded. Okay, it's a bounded set. Next, we have the definition of test functions. All right, so we have this special symbol d of omega for the set of test functions. What the set of test functions really is it's the set of functions, smooth functions with compact support in that omega. All right. So omega is by definition open, and so the functions have to be 0 before they get to the boundary, so that when you take the closure of the points where they're not 0, you don't accidentally go outside the boundary of omega. And the reason that we give it a new symbol d instead of considering just c infinity with 0, this 0 here means compact support, is because we, at a higher level, if you go further into the theory of distributions, you need to give it a certain topology on this, and it's not the normal topology you give to the set of smooth functions. Normally, we give the set of smooth functions the norm topology coming from the supremum norm, but we want to give the space of test functions, which is the same functions, a different topology, and it's a non-norm topology, so we don't really worry about it in this course. But we do, because we don't want to make a wrong definition, we do give you the correct definitions. We have these semi-norms. These are semi-norms because a non-zero function might still be 0 when you apply this function to it if its support is outside k, or maybe you have a constant function and then its derivative is 0, and so it's 0, but the function itself is not 0. So they're only semi-norms. And what we really want is we want to define distributions. So a distribution is a linear and continuous function from the test functions to the real numbers. In other words, it's a dual element to the test functions. And because of this continuity, the topology of the set is somewhat important, but we can just give you a direct definition or an equivalent characterization of what a continuity means for distributions. It means for all compact sets that lie in the domain, and different derivatives you could take, represented by multi-indices alpha, and you need some constants. And then for all test functions whose support is in this compact set K, you have a bound like this. So maybe we'll just do two very easy examples. So everyone's favorite distribution is the delta distribution, which is defined like so. Okay, it's just a valuation of the function at 0. So evaluate the function at 0, or sorry, the norm of the function at 0, or the absolute value of the function at 0, I should say, is of course less than or equal to the supremum. So for any compact set K and test function in K, the value of that function at 0 is of course less than its supremum, and this is by definition the supremum on K, I should say. 0. All right, this is its 0th semi-norm. So we have that the delta distribution obeys this inequality with just having one term in the sum and the constant being 1. Okay. More typical example is if you have a distribution f of 5. So these are distributions that are coming from functions. We'll talk about them more a little bit. This is, of course, the integral of f of phi, and it's the integral over k, because phi is by assumption of this definition of continuity a test function in k, so it's 0 outside k. And this is less than or equal to, if you just take the most brutal the supremum, I'll write it like this, supremum over k of the absolute value of f multiplied by the measure of k multiplied by the supremum of phi over k, and the supremum, all right, just, you approximate both of these functions from above by their supremums, and then you have an integral over k, which is the measure of k, and because it's a compact set, in particular a bounded set, this is a finite measure. So here you have your constant, and here you have just the 0th k semi-norm of phi again. Okay, so that's also an example of how you prove that the distributions of this form also have this continuity condition. And of course, there are other distributions that you might need to prove obey this continuity condition. So as I said, for any locally integrable function, there is a corresponding distribution called f of f, or ff, and it's given by integration against f. So previously, sometimes we've said that distributions are a generalization of integration in some sense. And so this is how you can treat a normal function as a distribution, is by integrating with it. And the important thing to know about this association is lemma 2.9, which is also called the fundamental theorem of the calculus of variations. And it says that this association is injective. So the only Yeah, so if two functions give the same distribution, then they have to be the same L1 local function, right? So that means that they're almost everywhere equal. So that's the definition of distribution. What can we say about distributions? So distributions, because they're in the dual space, they are also a vector space over R. So we can take the sum of two distributions. We can multiply a distribution by a scalar, by a real number, and it's just action like this. But we can also define some interesting operations on them. So we have what's called differentiation in the sense of distributions. So this is not a normal definition of differentiation. A normal definition of differentiation sort of has a quotient and a limit, right? It's something divided by h, limit h goes to 0. The definition here is not like this, right? It's given by this definition here. You take the negative of the distribution acting on the partial derivative, the partially derived test function. And why does it have this definition? So to understand all these definitions on distributions, or operations on distributions, we need to imagine that they come from distributions that look like this. So we want to understand how the corresponding distribution looks here. So the question is, what is the corresponding distribution for the partial derivative of little f, right? How does this distribution act? And how it acts is, of course, integration of the function, in this case, the partial derivative of f, against the test function over some domain. Now, because the test function vanishes inside the domain, we can apply partial integration, the partial integration formula that comes from the divergence theorem. And namely, we get negative the integral with the partial derivative now moved to the other factor, okay, over the same domain. So this is partial integration. But what is this? This is nothing other than minus f of the distribution associated to f acting on the partial derivative of the test function. So for distributions that come from functions, the association between the distribution that comes from a function and the distribution that comes from the derivative of that function is like this. And what we do is, for the derivative of derivative in the sense of distributions, is we say that this relationship should hold for all distributions, not just distributions that come from a function. All right, and that's how we make this definition, and that's how we make many of these definitions. So, for example, with this next one, multiplication with a smooth function, it's because, I'll just make some space here. If we look, how does the distribution of f times g act on this? Well, it's the integral of fg times the test function. And if we group it like this, we see that that is the distribution associated with f acting on g phi. So again, we take this relation that holds for distributions that come from functions, and we generalize it to say it should hold for all distributions. And that's how we make our definition. So differentiation is very important. Multiplication by a smooth function is not such an important operation. What is an important operation is convolution with a test function, g. So g should have compact support in particular. And it's defined as convolution of test function with pg, where pg is the reflection of g, right? So you need the sign change in its argument. What you should do as an exercise is you should try to prove for yourself that if f comes from a function convolved with g and it acts on f, that you get, you should try to prove that you get f of the distribution coming from the function f acting on 5 convolved with pg. right? Just as we had for these two examples. That's a good exercise for you to try yourself. Because, of course, that's where the definition comes from. What we have is this very nice lemma 2.7, is that the convolution of a distribution and a test function, even if it's a distribution that does not come from a function, the convolution after you convolve it with a smooth test function does come from a smooth function. Okay, so what do I mean by that? Any distribution f, there exists, let's say, a h such that g convolved with f is equal to the distribution coming from h, right? And this h is a smooth function. There exists h in the smooth functions such that this holds. So that's a really nice result and shows us why convolution is such a nice operator, because it gets us from a general distribution back to one of these special distributions coming from a function. And not only that, it comes from a very nice function. It comes from a smooth function. So that is why convolution is the best operator on distributions, and we use it everywhere. Okay. We also have this very nice result that the delta function, when you convolve it with a distribution f, there's a definition of the distribution of the convolution of two distributions together. So this is the convolution of a test function and a distribution. There's also a definition in the result of two distributions together. If you do that with the delta distribution, then you just get back the distribution itself. You should try to prove this result to make sure you understand the definitions. And I said one of the nice things about 2.7, lemma 2.7, is that you get back a function from a distribution. Another way to get back a function from a distribution, or how to undo this correspondence. We know how to go from a function to get the corresponding distribution. How can you go take the corresponding distribution and get back the function? What you can do is you can act the distribution on what's called mollifiers. So I've drawn them several times already, but a mollifier is a family of smooth functions, or functions of smooth support, of compact support. So lambda x epsilon is smooth. The support of it lies in the ball centered at x, a radius epsilon. And there's one more property. The area under each of these functions is always equal to 1. Right? So the idea is you should understand functions that are sort of coming towards 0, but they get taller as they come towards 0 in such a way that the area is always 1. And when you act a distribution on these functions and you take the limit as epsilon goes to 0, you'll get back the function that you started with if the distribution comes from a function. All right? If the distribution does not come from a function, you have no guarantee. Okay? It might not converge, etc. Maybe if you want an exercise there, try what happens with this limit if you take the delta distribution and apply a family of mollifiers to it. What is the function that you sort of get back? All right, you don't get a function back is what you'll see, but exactly how does that happen is a good exercise for you to see why you don't get a function back. Okay, so those are the basic operations on distributions. What do we use distributions for? So we defined a partial differentiation operator on distributions. So if you have a PDE, one thing you could do is you can say, what does this PDE, partial differential equation, look like applied to distributions, where instead of thinking of the partial derivative as the normal partial derivative of functions, you think of it as this partial derivative of distributions. So one of the nice things about our definition of the partial derivative of a distribution is that if you have a function that solves a PDE, its corresponding distribution will also solve the same PDE. All right, so why is that? Let's look at that. So let's suppose maybe I need to put a caveat here, a linear partial differential equation. Okay, so let's just take a solution to, I don't know, the transport equation. So we have a solution to the transport equation. Let's look at the transporter operator applied to the distribution corresponding to U. And how you understand any distribution is you see how it acts on a test function. So by definition, this should be the t derivative of f minus the x derivative of f acting on phi, and we said that this is the space of distributions is a vector space, just the vector space of functions. So this is the partial derivative of f acting on phi minus the partial derivative with respect to f acting on phi, like so. Now we have a definition of what this means. Right? It means this acting on the partial t derivative, of phi. Because these are linear operators, sometimes people put the minus sign inside, sometimes they put it outside. That's why I made the mistake there. So we have this. And let's look at what this is. This is the integral over the domain of minus partial t, of u multiplied by minus by partial t phi, and u multiplied by partial x phi. Now, phi is a test function, so we know that it's 0 near the boundary. That means we can apply, you guessed it, integration by parts. That will give us partial t u phi minus partial x u multiplied by phi. And if you just factor the phi out, what do you have there? You have nothing other than 0. All right, so this is why partial differential equations in the sense of distributions generalize partial differential equations in the sense of functions. Because any function that solves a PDE, a linear PDE, its corresponding distribution will as well. Notice that we needed the assumption of linearity, of it being linear, in order to apply the integration by parts formula to bring it across to U. All right, if it's nonlinear, then that operation doesn't work, and then there's no correspondence between solutions of partial differential equations and partial differential equations for the distributions. All right, so this distributions are a technique that work on linear partial differential equations. All right, but that's okay because a lot of equations are linear partial differential equations. And so in this sense, it's really nice to look for solutions among distributions because distributions have all the derivatives. If we look up at the definition here, we can see that we can put as many derivatives onto the test function as we want because test functions are assumed by assumption are smooth functions. They have all the derivatives. So that means differentiation in the sense of distributions can occur as many times as you like. There's none of this needing to assume the solution to be C2 or something for distributions. All right, you just say, can this be solved in the space of distributions or not? So it's the most general setting for linear partial differential equations. And what's nice is that you can consider discontinuous solutions, because the only assumption to go from a function to a distribution is that it's L1 local, right? It's locally integrable. So that includes discontinuous functions. That includes functions with point singularities. That includes some point singularities, right? If they're integral ones, and so on. So it allows us to consider discontinuous boundary conditions. It also allows us to consider things like we had for the fundamental solution, where they have a singularity, and then it's equal to, when you apply the operator in the sense of distributions, you get a delta distribution. Right, so that's also nice. And then, like what we found with the Laplace equation, was, okay, we try to solve distributions. We try to solve the Laplace equation in the setting of distributions. And what it turns out, because of Weil's lemma, is that anything that solves the Laplace equation in the space of distributions actually comes from a smooth function. So it sort of gives even though we were looking in the broadest possible broadest possible space, only very nice solutions were possible. So that's a really, really strong result. And that's the sort of things that you can find. All right. You might think, okay, I threw away all the regularity at the beginning. I'm looking at this really general thing. You can bring back some regularity at the end sometimes, after the problem. So that's what weak solutions mean. That. So we can look at weak solutions to the transport equation and the 1D wave equation. We both did this. Because these are linear partial differential equations, this makes perfect sense. Okay, so let's just go ahead and show that, let's say, this function here solves the, I don't know, transport equation. Yeah, that'll go. So let's show x minus t solves the transport equation in the sense of distributions. Okay. Maybe I'll use a lowercase f so that we can use uppercase F for distributions and lowercase f for functions, right? So show this function solves the distribution in the sense, equation in the sense of distributions. So let's say that the corresponding function, corresponding distribution is f. So how does f act on a function phi? Well, it acts on a function phi by integrating over all of space of the function f. I used a different phi, xt dx dt. Okay. So that's the corresponding distribution. And so what we need to do is we want to show that f solves the equation in the sense of distributions. So we should calculate plus applied to f. And how does this distribution act on phi for any phi, any test function phi? Well, by definition, this is f acting on negative t derivative of phi, negative x derivative of phi. And then by the definition of the corresponding distribution, this is the integral over r squared of f of x minus t, and so on. Now, the point is that we've already seen that these functions solve, let's say, the transport equation when it was differentiable. So the point I want to make now is I don't want to assume anything about f. Okay, I have to assume it's locally integrable so that this expression makes sense. But I'm not going to assume that it's differentiable. Right, so I can't apply the partial integration like I did previously. How can I still prove that this always comes out to 0 so that I can show that f, capital F, always solves the transport equation for distributions in the sense of distributions? And how I can do that is I can make a coordinate transformation. So what I can do is I can say let u equals x minus t and let v equal x plus t, for instance. Right, so this is a coordinate transformation of the plane. And then we need to do some calculations. So the partial derivative of phi with respect to t, what's that going to be? That's going to be, well, I'll just write it out. Applying our beloved chain rule. So u with respect to t is minus the u derivative of phi, and v with respect to t is plus the v derivative of phi, like so. And then in a similar way, the x derivative. So here we're going to have the u derivative of phi plus the v derivative of phi. And we also need to calculate what dx dt is. Okay. Well, I know it's going to be equal to 0 in the end, so I'm not so inclined to make this coordinate transformation. But what is it? It's 1. Yeah, minus 1, 1, 1, which is 2 du dv, I believe. So continuing on from above, we'll have the integral over r squared, f of u, and then negative t dt will give us like so, and then the negative of u will give us this 2 du dv. This and this cancels. And so this is the integral over r of f of u, the integral over r of negative 4, the partial derivative of v dv du. Because this is a test function, when you integrate this, you get 0. And so this is then the integral of f of u multiplied by 0 du, which is also 0. So what do we conclude from this calculation? We conclude that this distribution here, this orange distribution, acting on any test function gives 0, and therefore we say that this is the 0 distribution, or in other words, f solves the transport equation in the sense of distributions, right? Because we have that that is equal to 0 for this distribution f. So the distribution corresponding to this function f, even not assuming this function is differentiable, still solves the transport equation. Okay, and so when we say that if f is just, say, continuous, or f is just, say, L1 local, we say that the function solves it in the weak sense because the corresponding distribution solves the problem. Right, and so that's what we mean by weak solutions to linear problems. Yeah. And we did some exercises. There's an exercise in the script, 2.10. The solution to this is in the exercises from last year, if you want to go look them up. We also did our own exercise 18, which is very similar to which also related to distributions and the transport equation. If you want to go back and revisit that, those are quite technical results because we wanted to prove something even more. We wanted to find solutions to the transport equation for distributions, even when the distributions don't correspond to functions. So this distribution f corresponded to this function here, f of x minus t, but we solved it even more generality in these two exercises. And for exercise 42, I believe that's weak solutions to the 1D wave equation. Okay, so now we come to the last slide. Almost there, everyone. We also had this idea of weak solutions for first-order systems when for nonlinear systems. So this is a slightly different meaning of weak solution, right? Because these are nonlinear PDEs, it's not clear how to apply distributions, though I believe there is a theory of distributions for nonlinear partial differential equations, but that's well beyond this course. I don't even know this theory. But in this section 1.4, we had the scalar conservation PDEs. In particular, we had Berger's equation, which is u dot plus u times the x derivative of u is equal to 0. That's Berger's equation. And we applied the method of characteristics to this equation, and we saw that the solution in terms of characteristics was quite simple, but for some initial conditions, there were no solutions. Or for some initial conditions, there were multiple solutions. So what were we to do? Well, what we did is we allowed what we called weak solutions, which are slightly different from weak solutions in the sense of distributions. So by characteristics, we saw for some conditions no C1 solutions were possible. C1 is sort of the natural regularity for this problem. And so what we did is we looked for solutions that were C1, except we allowed what we call certain singularities or discontinuities. So we allowed curves in the domain where the function was not C1. And so instead of what we required at those points was certain desirable properties. So for example, we had the Rakhine-Huguenot condition and we had the lax entropy conditions. Right? Those were both conditions that had to hold at every point of the so-called discontinuity along this curve where the function was not required to be C1. So we replaced satisfying the partial differential equation at these points with satisfying some other condition that were inspired by physics. And what was notable, and what connects this to previous, is that the properties that were required to hold were integral properties, right? So in the case of the Rakhine-Huguenot equation, this was some conservation of mass. And so the integral over from one side of the discontinuity to the other side of the discontinuity had to be not changing in time, for instance, right? That the total mass had to be not changing in time. Of course, it's a bit annoying to work with integral conditions, so these were then reduced to sort of algebraic conditions that were easy to check. But you should remember that the properties, let's just look at them now, in fact, under weak solutions. The property here that we required was that this should be 0, that this should not be changing in time. Okay, and then from that, we were able to turn it into some terms and rearrange these into an algebraic expression that had to hold. But originally, what we wanted was that it was not changing, and it was under an integrable sign, and so that for that reason we also called these weak solutions. And we did manage to prove some nice theorem or almost proved this nice theorem, that if you have an initial condition, if you have, the function f in the conservation law, which is half u squared, was strictly convex. So, for example, Berger's equation holds this property, and that the initial condition was bounded and integrable. Then there was a unique solution in the sense of weak solutions defined for these problems of the scalar conservation law, obeying the Rankine-Huguenot and the lax entropy conditions. So I mentioned that the Rankine-Huguenot was a conservation of mass property. The lax entropy condition, remember, was this condition that characteristics were not allowed to emerge from the line of discontinuity. Characteristics could end on the line of discontinuity, but they were not allowed to begin on the line of discontinuity. So that was the lax entropy condition. And under these two, then there was a unique solution. So if you only wanted to look for strong solutions, that is, you only wanted to look for solutions that were everywhere C1, then the method of characteristics would find those solutions. But we saw for some initial conditions, there were no such solutions. So we had to change what regularity we were requiring. We required weaker regularity in that we're allowing functions that are C1, but they have discontinuities. And then we had too many solutions, right? There were exercises, I believe it's 7, definitely, was asking you to find multiple solutions to a problem. We had too many solutions, so we then imposed some conditions that come from physics, and then we indeed had a unique solution. So that's what weak solutions for first-order systems were about, particularly for this conservation laws, which are nonlinear partial differential equations. For linear partial differential equations, we use distributions. So that sort of covers distributions and weak solutions, and that finishes the revision lecture. So, of course, this is not the finish of your revision. You should indeed go back and look at the proofs, understand the ideas, be able to reproduce the important proofs yourself. And, of course, you can use the recorded lecture videos and, of course, send emails to myself and Professor Schmidt, or perhaps if you're watching this in the future, to whoever your instructor and tutor are. And so I wish you good preparation for the exams.